Okay, now we're going to continue on the second topics, still with the derivative and still under the image enhancement. But before this, we are not talking about the gradient operator, which is a self-solvable especially. Now we are going to move on for the next operator, which is coming from the derivative for second order. So the topics will be in the sharpening things, sharpening of the image. All right, so we'll back that where we right now. So we already still at spatial domain here, and we had spatial filtering, and we had the sharpening filter, and still at derivative. We already completed the first order gradient, and we are going to work on the second order Laplacian. So this is a second order derivative. So the first order we learned about the Sobel, period I don't touch, and just a big thing about Robert. Right. So now we are going to concentrate on the Laplacian for the second order. Again, this is the thing that to remind that we have learned so far about smoothing and sharpening, right? Sharpening not yet, so this is the one that we're going to talk about, sharpening. So again, smoothing is related to the integration process, where if you go back to your basic mathematics, we have that particular the integrations and integral. Okay, so this is kind of examples of the results from the image that we use the sharpening filters. So you can see the difference, especially on the edge, or on the edge of the object is getting clearer, so it's even sharper. This is how they are doing it, because normally when you use your phone to do the sharpening process, I mean to look at the image, you can see the image is getting sharper. All right. Okay, so we go back to the types of regions that we learned before. So you can see here the different types of regions that we have. There are three types basically. One is the normal one, constant intensity regions, more or less are the same. And then the second one is actually intensity RAM, and just a bit of RAM between the lights and the darker version, the darker area over here, dark areas. You can see the numbers is getting lower because of the darker version on the pixels. And the last one is the intensity that is very steep, or sharp edges they call it, because you can see the difference between the dark version and the lighter version from the image itself, right? So these are the three types of the regions. So what is a sharpening filter? All right, so again, when we learn about the convolution, there's a kernel or mask or filter that we can use to do the neighborhood process. The sharpening must be accomplished by spatial differentiation, so it means the on the spatial, right? Then you have to do the differentiation, this is derivative operator. So that's why over here I keep on telling you guys that the smoothing is more the integration process, whereas the sharpening is a opposite of the smoothing process, which is the derivation. So this is a special differentiation, and so in the mathematics sides I do not going to explore or elaborate in the slides. So we're going to get on the result of the profilings after you have all this image fxy being differentiated to find out what is the kernel of those things. All right. So what does that mean for this sharpening filter? The function is to highlight the details of an image by intensity, where it enhancing the edge, which is the edge crisping algorithm. So it's going to find out the edge and what we call that to highlight the details of the edge by the intensity lah. The intensity is the number from the, for example, just now we have 0 to 255, right? 0 is very dark, 255 is very bright. So that will be the intensity for the grayscale image. Okay, so for the sharpening filters that we're going to learn, we're going to learn about roughly two. HIBOS is part of Unsharp masking. So one thing that we're going to use is, they call it Laplacian operator. This is a second order derivative. Remember that the gradient before this that we learned is actually a first order derivative. So the second one is going to be a Laplacian, which is a kernel used to enhance the edge. Gradient also to find the edge. It's just more or less nearly the same, but it is a second derivations to perform on the image. Alright, and the second one is unsharp masking. Unsharp masking is a masking, we call it unsharp masking, and later you can know, you can understand about the high boost filtering, which is to boost up this one, the unsharp masking. Alright, this is just the image here. We have the mask here. This is actually the Laplacian mask, so we're going to look that one later. And then this is actually the results for the image when you are running under when you do the filtering for sharpening filter. So you can see this is like, for example, this is the smoothing. Okay, this is a blurred image by Gaussian. This is actually ABC. This is the mask, and then this is result on unmasking now. So this is actually all the results for the sharpening. Alright, so we go back to this theory again. Alright, so the first derivative, we already talked about this one in gradient. So let's look at the second derivative. So the second derivative, this part. Alright, so this is the second derivative. Okay, when it has a ramp, this one, right? It has a ramp from 0 to, this is actually 150, I think it's 150, right? There's a ramp over there. So first derivative, of course, there's a ramp is going to be a constant point. Okay, this is a constant point. Alright, this is constant point. But for the second derivative, right, you are going to use the same image gradient profile and do the second derivative. You found out that basically the positive transition, okay, is only associated with the dark side of the edge. So the first one here, you're going to find out the positive one over here when it's going from dark to the light one, and then you have to have another version over here. This is a negative one, this is a positive one, right? So you see positive at the transition associated with the dark sides of the edge. So this is dark side. Negative at the transition associated with the light side of the edge. So this is going to be your this is the area, and this is another area. This is a area that always 0, and then you have the ramp. It's going to be a positive for the black area to dark, black area to white, and then you have the negative when it has black to white. Okay, this is the ramping here. Okay, this is another ramp here. Okay, this is actually another profiling. All right. So 0 along the ramp, okay, the ramp and areas of constant gradient. So constant along the gradient is this one, and along the ramp is this one. Okay, the ramp is at the center here, right? This is the center ramp. So going down here, this is from the ramping from black, and then going down to white. Then you have this particular profile, right? So what you can conclude from this one, for the second derivative, okay, for the second derivative, sign of the second derivative can be used to determine whether an edge pixelized on the dark or light side of the edge. So before this one, you know this is a dark image, dark pixels, or after this one, negative one, this is always a lighter image, right? So this is the sign of second derivative. So additional properties that you can try to look at is actually that it produces two values for every edge in an image. So this is an edge, right? So there will be two values, one here and one here. Alright, so an imaginary straight line joining the extreme positive and negative values would cross 0. So if you take this one and then make it a line, and then crossing here would be the center or the midpoint on the edge. So you can get very, very centered point at the edge here. Alright, to this one when you do the imaginary line. Okay, that would be a second derivative. So first derivative, we already talked about our ingredient. Okay, these are the Laplacian kernel, which is the second derivative. So I'm not going to talk about the mathematics, so we just give you the kernels normally that are being used for the Laplacian. So this is called Laplacian kernel, which is second derivative. So this is normally being used. This is the kernel 0, 1, 0, 1, negative 4. You can see this is the negative 4, negative 8. So if this is positive, the rest is a negative 4, and because of that, the sum inside this element inside the kernel is always 0. So 4 minus 1 minus 1 minus 1 is 0, total 0. Same goes to this one, right? Same goes to this one. Alright, so this is a 4 different example of Laplacian kernel. So what do you do? Okay, when you run an image with this Laplacian kernel, right, so it's going to find the edge of the image. So Laplacian image has grayish edge lines and other discontinuities all superimposed on the dark and features background. So this is going to be the results, Laplacian image. Not really good, right? So you still cannot see the real one. This is just like a black grayish one, like, okay. So Laplacian operator will highlight sharp intensity. So wherever transition, right, I mean the edge, it will going to highlight okay, and image and de-emphasize regions of slowly varying intensity, so that it's not going to take care of these slowly varying intensities. So it's going to just concentrate with the different intensities changes on that. Alright, so normally it's on the edge. Okay, what else? So how we are going to complete the process? Alright, to do the sharpening filter complete one, right? So what we have to do is we have to add the result just now, this one, right? So we have to add this one with the input image. Okay, so we have this one, you have add this input image, and then finally you can see the image is getting sharper. You look at the dot here, is even sharper compared to this one. So after you have the mask, you get the results, and then the result is going to be add with the original image. Okay, so this is the results. This is the input, and after you have the Laplacian plus the input, you got this result. This is even sharper. You can see the edge here is sharper, right, compared to this one. So this is how you are using a Laplacian kernel to make your image sharper. Right, let's move on. Okay, I go back to this particular image, right? So I just run the program with MATLAB with the mask, I mean the kernel mask. I just want to see what the mask doing basically on the image. So you can see that it's actually highlighted, right? This is the highlighted version of the results. If I run this image with this mask, right? So it's going to make the intensity higher, especially on the different edge. I mean different there's a changes on the edge over here. So this is very dark going up, right? So you can see the result is actually highlighting the edge based on this one. So the high it is going to highlight higher than that. So this is really still there's a changes, right? But it's still lower compared to this one. So this is the constant intensity region. So it's very small. So even though there's actually some of the changes, but that's not really what you call that, very clear, all right, preferences on that. So there is going to be very small numbers, right? So for the intensity ramp, you can see here is the one that have numbers for the ramp intensity. Okay, this is the where you, when you do result, you get the Laplace kernel over here. There you can see this is the edge area. Alright, so this is the result part for the result part. You can use MATLAB to run it. And again, you have to do convolution again. So this image go to convolution. So this is not going to be two sections, dx and dy. So this is a complete one. So if you rotate 180 degree, right, you rotate this one to this one, rotate to this one to this one, this one to this one, this one to this one, you also still get the same one. So at the end you are going to have the convolution with the same image over here. Alright, so this is actually 180. This is a convolution process. Alright, so that will be the Laplacian. Okay, the next one we're going to learn is they call it Unsharp masking. Okay, what is it? Yeah, so Unsharp masking is another type of mask, right? Where you want to find it, you have to find the method is we have to find out first. Alright, is a hybrid filter technique which remove both impulse and Gaussian noise. This is actually a noise lah. Rather than before this, I share you guys with the salt and pepper noise. But right now you are going to you are going to learn about the impulse and Gaussian noise. If you Google these two things, it nearly the same like the salt and pepper, but there's a difference on that. It's actually a bit blur on the noise that we have based on the impulse and Gaussian noise. Alright, so again, because of this the topics that we're learning is about sharpening, right? So it's still by using this unsharp masking is also enhance the edges. So the result, which is the sharpened image, right? So for sharpened image, the result after you have it, you get the results, right? Is getting by subtracting the unsharp image version from the original image. Okay, so you have the image here, and then when you blur the image, you minus up the blur from the original image. So it's a bit different from the sharp filtering Laplacian just now. Okay, so this is a minus of sharp version. So you have to blur first the image, and then you minus up from the image, and then you get the unsharp masking here. Alright, so let's move forward to look at why and how you need to do when you want to do the unsharp masking. So this is a sharp version, right? This is the original image. This is the blurred image. You have to minus. This is a bar over here. Alright. Procedure for implementing an unsharp mask is, first you have to read the image here, and then blur the original image. You have to blur, right? And then you have to subtract the blurred image from the original, and then you have to add the mask to original. So this is the mask. Later you have to put back in the original. Okay, you have to put back in the original. So it's going to be like this, right? You have the image here, you have the blurred version over here. Alright, so you have fx minus fxy. Alright, so this is the one. Then you got the mask here, and then finally you have to add the mask to the original. Right, what does it mean here? You have to add the mask to the original. This is the original again, and then you got the result. This is the results for your input image after you run the unsharp masking. And so this is going to be your image. If you can see, okay, this is the example. This is your image, right? This is your input image, and then you are going to blur it by smoothing process, and then you have to minus up this image. Okay, minus up the blurred image, then you got this image at the end. This is unsharp mask. You can see this is the normal unsharp mask. The first one, this is the unsharp mask. They call it, this is a mask, unsharp mask. Alright, you can see already the edge is actually been highlighted over here. Okay, it's highlighted. It's just like an embossed version. You can see the edge is getting clearer. Alright, then when you want to do the high boost filtering, okay, high boost filtering, you have to understand this function again. So this is the unsharp mask, this one, right? That's also here. And then you have the results based on the sharpened signal is from here. This is unsharp mask. Then you use back this unsharp mask to get the result here. This is going to be your result for the sharp using the unsharp mask. Okay, K is just a coefficient. So if it is 1, okay, if it is 1, right? So this is an unsharp mask. If you give more than one, right, you are going to increase the mask coefficient, means that you are going to sharpen more the signals, means that you can see that the edge is getting sharper, right? This is sharper, means you are going to boost the sharpened image. Okay, the signals is going to be boost after, if you are going to include K is more than 1. So if only 1, then it's go back to the unsharp mask version. Alright, so this is going to be the meanings of the unsharp masking. Alright, so K, if you see, if you add more 4.5 over here for the K, alright, the image for the what I call it, the edge is going to be even sharper, even like embossed. I mean, it's like something like going up. You can see from the result of the sharpening process. Okay, so you have first one just now, the Laplacian, alright, and then you have the unsharp masking, which is this one, and then you have to use this one as your results to get the sharp image, and then this is going to be based on unsharp masking or high boost filtering based on the K, the coefficient. Alright, then you know that what will be your results from the input. Okay, so again, this is the one, this is unsharp, so this is high boost, so this is unsharp mask. Then you go back this one with one is going to be the unsharp masking results, and then if you more than one, you are going to have the high boost filtering. That's simple. Okay, this is just example. All right, so this is your input image. This is a semi-spheroid but darker. All right, so A is Laplacian. This is Laplacian, if I'm not mistaken. This is Laplacian, and then this is actually going to be this just unsharp masking, and then you can see if you put more than one on the K, right, you're going to have a high boosters on the sharp. This is, they call it high boost filtering, right? So you're going to get another image which is the image is much clearer, sharper. This is just the results on that. Okay, so just to conclude, this is quite simple. For sharpening process, right, you must use the concept of spatial differentiation, and it must be on the second order derivative, because the first one is gradient just now, and then there are two kernels that two operators that we're going to learn. First one is the Laplacian, and then the second one is the unsharp masking, which is after that we are going to have the high boost. This is nearly the same, but just the coefficient is a bit different. All right, so I think that's all for the sharpening lectures for this site. This is the Laplacian. All right, thank you very much. See you guys next time. Thank you.